Yesterday, we talked about colors. What are the primary colors of light? Red, green, and blue. Okay. Now, if I had the ability to click a button and make all these lights red, that'd be cool. But we'd see things differently. Most lights we have in here are white, so it has all the colors. Could put tissue paper over all the lights, but that'd be a lot of work. So what I'm going to do is going to give you filter paper, and you're going to wear like red tinted sunglasses. That has the same effect. Okay. So double there.
I mean, there's 43 different.
Seen better days.
That's real.
Oh, don't have enough. Easy. All right. So, quick disclaimer on this one. What I passed out to you is not high quality filter paper. You see the difference here in the quality here. Like, so this is high quality. I've got a lot of this stuff, so that's what you got. You don't have much of this. So this isn't the best. Well, that's not too bad. So if you look around the room, you can see different stuff. If you look at something that is red, it looks red. Okay. So white light's coming down typically, reflecting off of this. This is absorbing what colors? Absorbing green and red. And it reflects what?
Red.
Red. Your filter paper allows what to get through?
Red.
Red to get through. So you see red. Okay? If you look at something blue, you look at something blue, it now looks black. Okay, yes? Does that make sense? So, what color is that reflecting? Reflecting blue. What color is this not allowing to get through? Blue. So it looks black. So if this was red light coming from here, there'd be no blue light to reflect. It'd only absorb red. So it looked black.
Why is yellow
Hang on to that.
every color looks there?
Ooh, great question. Okay, if you look at look at this. Look at the green bucket.
Oh, so see the
Green bucket looks what?
It's definitely black. Top two buckets.
Green bucket. Good? Okay. Now, so if you look at, we're going to have a little conversation here. If you look at the yellow chemical shower or the top of the ladder, okay, you're going to say it looks yellow. And I'm going to say, no, it is definitely a shade of red. And you're like, no, it's not. And then I say, okay, look at this piece of white paper. What does it look like? You're going to say white. And I'm going to say, nope, it looks kind of reddish, pinkish. Okay? Because if you compared it to this, it would look red. Okay? Color, a lot of times, depends on what you're comparing it to. So you can put down your red filter paper. Actually, pass the red filter paper up. So, if you had red light and you had a red object, so you only have red light coming from it, the red object in white light would reflect red, so you're going to see red. Here, yellow, you don't have red coming from the light source. In white light, it would reflect the primary colors green and red. It would be seen as red because that's the only thing coming from the red light bulb. Good with that? Okay. So, color, a lot of the time, depends on what you are comparing. Remember this whole conversation? Okay. All right. Let me show you some things that are interesting. This right here and this right here are the same color. Identical shades. And you're like, don't believe it. Okay. And you're like, prove it. I'm like, not a problem. We can prove it. So we're going to take it. And I'm going to clip this. The same color. You see that? So you're like, what? And then you compare it to white, and it's like, ugh. That's ugly. Okay, so you see blue down here because you're comparing it to this background. You see red here because you're comparing it to the background. Remember yesterday with the filters, I was like, hey, you're going to say it looks orange. I'm like, no, it's not, it's red. Because it was being compared to magenta when I put the red filter up there. Like, okay, yeah, that is red. If you go into a paint store and you get a a color swath of like different shades, it's going to be really difficult for you to figure out what color is going to look good in the paint store. Because you would never think that you'd pick out that color to make that look blue. Or sorry, make that look red. Or in this case, blue. That makes sense. Like, a lot of times color is determined by what you're comparing it to. So you're like, you really need to take that color swab and like go to your house and like get several of them, like put them on there, like what is that going to look like? Does that make sense? Okay. That square and that square are identical colors. So what was orange is really brown. Do that. Okay, this one's fairly easy to see. This shade of gray and this shade of gray are identical. You can put your finger over that, the crease, and kind of see that. Or I should be able to do this one. This is. You know that? Okay. This is like one of my favorites. A and B are identical shades of gray. Ready? Which one do you want me to clip? A or B?
B.
Let's see.
You see that? Is that not crazy? Go clip A. Get in there. And we made that square A. Good with that. This bar here is the same shade of gray all the way through. The only thing that's different is the background. See that? Good? How are we doing there? So, color, that's interesting. All right. Try that question. Tell your neighbor what you think. Correct answer is? Oh, no. Tell your neighbor. What do you say? Okay, red light is the source. A green plant would reflect what color in white light? Green. It absorb what colors? What primary colors would it absorb? What would it absorb? Red and blue. So if you only have red light, it's absorbing red light and reflecting nothing. There's nothing more to reflect, so it's going to look black. Okay with that? So check this out. Have you seen modern grow lights? Like what color are the glow, like the grow lights? Yes, no. Nobody has a grow light at home. Have you seen them like look magenta? If you flip them up, they've got red and blue LED lights. Yes, no, maybe so. You know what I'm talking like any. Okay. Modern day grow lights have red and blue LED lights. What in the world? Why would they do that? I mean, like you need to do like photosynthesis, right? Like that's the whole point. Like, what does a plant do to the sunlight to do photosynthesis? It absorbs. What colors are being absorbed by a plant? So it'd be interesting to like it would be absorbing. Okay, it reflects what? Green. It absorbs blue and red. So to actually have a white grow light is inefficient because it reflects the green. It doesn't use it. We see green. So if it's just the magenta, it's absorbing all of that. Have you ever seen a plant? I'm hoping I told first hour this. I didn't look down below, but like the greenhouse room thing right below it, like in the science wing, has these grow lights. I don't know if they're on, but if you ever look at a plant under one of these grow lights, it looks dead. Like it looks sickly because there's no light to reflect it. It's just like, oh man, this thing's. But then when you take it out into white light, it's like, oh, like I am like a thriving plant. But under the grow light, it looks horrible because there's no light that it's reflecting. You guys do not seem impressed. This is like a revelation to me. Like, no. All right. What would a green leaf look like under a yellow light? Tell your neighbor. Correct answer would be green. Yes?
Yeah.
Yep. All right. Blue jeans under a yellow light bulb. Tell your neighbor. Correct answer? Blue jeans under yellow light bulb. Yellow is what two primary colors? Red and green. Blue jeans are going to reflect blue, but there's no blue to reflect, so they'll look black. True story. I have a pair of navy blue pants that my closet has a warm light bulb. Like you have cool light white and like warm white light has a cool. Sorry, it's a warm light, so it's a little more yellowish tint. I cannot tell if these navy blue pants are black or blue in the light of my closet. Like I have to walk outside and I'm like, shoot, wrong pants. I've done it enough that I've written on the tag navy blue. Like you cannot tell. It looks black until you go out in the sunlight. Okay? So heads up. Good? All right. We'll give this a shot. All right. So. This kind of optical illusion type stuff.
Oh, double sided.
Nice.
Go Dr. Carlson's.
The outlet of the school, otherwise.
Okay, so you get those like this.
All right. So you have this is kind of funsies. You have a blind spot where your optical nerve goes to your brain. Okay, right here. Right there, there can't be any rods and cones because we have hardware that's going to your, like, that makes sense, like you got an extension cord right there that's plugged in. So you can find that. So you're looking at, flip it over to the side that just has green and blue. You're going to, sorry, green and yellow, sorry. Close your left eye and stare at the cross mark. So put the cross on the left-hand side. So you're looking at this side, put the cross on the left-hand side. Close your left eye and stare at the cross mark in the diagram with your right eye. Off to the right, you should be able to see the dot. Don't look at it, just notice it. That it is on your peripheral view. Now slowly take your piece of paper and move it closer to your face. At some point, don't look straight at the black dot. Look at the plus, but at some point that black dot will disappear. And that's where your blind spot is. Okay, there's some. Don't look right at it. There's just one point at which it goes away. Now, if you do it with this, like do it on the one that's down below that, the line, what your brain does is it actually will connect it and make a straight line. Like the dot will disappear and you'll just see a straight line. You see that? Okay. You can do the same thing with the other side. It'll make the yellow dot a red dot. Isn't that crazy? Okay. And then this one is just fun. It's like, you just look at it, it's like fills in. I don't know what looks better on the screen. Hold it away from you. On the blue.
Some of those squares should be turned like that.
Yeah, it turns, some of those dots turn blue. Do that?
I see.
At a certain distance, like if it's too close, if it's too far away, it doesn't. Well, it does work. All right.
Some of them are concerned that.
All right. If you can pass those up, please.
Yeah,
Some fun optical stuff.
right now. What is that? Thank you. I need to take glasses. My eyes are getting worse. All right. I need braces.
That's the lake.
Intense metro. Yeah. I was relegated to do some stuff.
Okay, what I have here are two polarization filters. Okay. Put them on top of each other. It's like, whoa, it got darker. Couldn't see that coming. But watch what happens when I rotate it by 90 degrees.
What the?
Not magic, it's physics. Okay? Now, here's how this works. So, hang on tight. Okay, so light is a wave, yes, electromagnetic wave. Okay, so wave, okay, so normal light is unpolarized, meaning it's going all over the place. Okay, this is going to represent our polarization filter. Okay, and we're going to cause light. We're going to cause light to pass through it. Okay, and so when light goes, unpolarized light goes through, what gets through up and down. Does that make sense? Okay. So this doesn't get through. This part does. Okay. Over here, where I'm at is unpolarized. Over here, this is polarized light. And it only goes one direction. So, thank you very much. How can we make two polarization lenses? Thank you very much. Cancel all light out. We could do what? Rotate by 90 degrees, yes? So, okay. Pass. We have one pass. Buddy up. And buddy up and cancel. You can try it.
Wait, did you?
I got the reference.
I think they're both supposed to be polarized. And you just turn one.
I want it.
Okay. So you see how you're canceling it out? Okay. You need to buddy up with somebody. There needs to be two of them to cancel out. You need two of them. You need two to cancel out.
Now rotate your
Put it up to your eye. Look at this, right?
and then rotate it.
See how
Okay. Now, where we find polarized light happen in nature is when light is reflected off of a non-metallic surface at a really shallow angle. Okay. So have you ever skipped rocks before? Okay. You're not gonna try to skip rocks by throwing the rock straight in. Like you're gonna try to throw it at a shallow angle. Yes. Okay. If light skips off of a surface, a non-metallic surface at a shallow angle, the light that comes off is polarized. And you can take your polarization filter and cancel it out. Okay? Look around the room. Don't look toward this way, but look around the room at non-metallic surfaces that have a reflection and rotate that polarization filter, just one of them, and you should be able to see things change. Like the glare, the reflection on the floor, like look on the floor. Look around the room. You're not look okay. So if I'm looking straight away into the glare of the reflection off of the glass here, that's not going to work because that's like me trying to skip a rock so like straight onto that thing. I want it to like bounce off. Good with that? Okay. So like floor, off the tabletops, off the glass. Okay, good. So when you are fishing, this could be beneficial. Good with that? Okay, takes the litter off of the Okay? If you look at your cell phone calculators, liquid crystal displays, LCD, those are polarized. Okay, so look at your, like, pull out your phone, rotate it, look at screens. Some of the pixels are polarized, so some of them are gonna get different colors, like depending on the design of the calculator and the screen of your phone, you're gonna get different colors coming out. Good with that? Okay. So different colors, as you rotate it, different pixels are being canceled out, so it's going to come out like magenta, cyan, and yellow, depending on how you angle it. It depends on how your phone is organized and designed. Okay? You can also get 3D movies. Your 3D glasses have you have a different projector projecting a polarized image, and it's going to cancel out one of your views. The way you have depth perception is each eye sees slightly different. It'd be really hard for you to catch a ball with one eye. You would struggle with the depth perception. You have two eyes giving you a slightly different vantage point, and so that's what 3D movies do for us, is they give each eye that different vantage point that looks like it's coming at us. I don't have the technology to do that, but I do have the old school way. If you could pass up those pass those lenses up. Okay, put the blue side on your right eye. Blue side on the right eye.
Yeah, it is copper.
Blue on the right
It's just
side.
Yeah, blue on the right side. Yeah.
No, look, it turns you blind. Take this one and put it
Okay.
That's the one. You go blind. I'm serious. Ow. Right. You can't see things.
Okay.
Oh.
So so you guys have pretty cheap ones. I've got this is like high quality. One side is red, the other side's cyan. Why would they use cyan instead of blue? It's the opposite. Like red cancels out green and blue, and cyan allows green and blue to go through, cancels out red. Okay.
Looks like going this way. You can try it. Ooh.
Okay, you ready? It gets better. So, turns out, skylight, sunlight, the sky is polarized. I can't demonstrate this because it's a cloudy day today. But if you have polarized sunglasses on a clear blue day, you can see at 90 degrees to the sun. If you have polarized sunglasses and like tilt it by 90 degrees, you can see how the sky goes from this color to this color. You can use that with cameras to like make clouds like pop out like it's contrast. Okay? No homework. Have a good weekend.
It's so rad for me. You don't have to teach me colors. Right, Bailey.